Namaste to all. Good evening, those who are in Nepal, and good morning, those who are in Canada. As in Nepal, we are celebrating World Meteorological Day as a part of Nepal National Water and Weather Week. Yesterday, we celebrated World Water Day, and it's an honor to have Scott Munro here with us as a key speaker or presenter. And today, we are celebrating World Meteorological Day with the theme of early warning and early action, hydrometeorological and climate information for disaster risk reduction. So as my part to introduce Professor Scott Munro, I'm truly honored, in fact, to introduce him. He is a Emeritus Professor of Geography at the University of Toronto. He did his Ph.D. from McMaster University in 1975 on heat transfer to melting ice on Peyto Glacier. His teaching interests are basically in basic and advanced climatology, climate change, urban climate, glaciology, the regional geography of Canada, and graduate student supervision. He's recently collaborating with the Center for Hydrology, University of Saskatchewan, for making his research data on Peyto Glacier available to other investigators. His research has been recognized very well through his publications and many other places. But one recognition I'd like to particularly mention over here, there is a new proglacial lake has formed recently at the tongue of Peyto Glacier that increases in size every year. And it has been named after Munro's name as a Lake Munro by University of Saskatchewan Center for Hydrology to honor his research contribution to the glacier basin. Here, I sincerely express my gratitude to Professor John Pomeroy, Director of Global Water Future and Center for Hydrology, University of Saskatchewan, for connecting Dr. Munro with me for my PhD research at the Canadian Rockies. I've got a great opportunity to learn from him and collaborate with him, continuing my research at Peyto Glacier. So with this brief introduction, I'd like to request Dr. Scott Munro to make his presentation. Over to you, Scott.
Okay, first of all, I'd just like to express my appreciation to the Small Earth Nepal, its supporting agencies, and to Dr. Pradanaga in particular for the invitation to speak to you this evening. As the introduction shows, my association with Peyto goes back a long time, such that I can remember things that most other people have never experienced in the basin. I'm going to organize this talk in two ways. No, not two ways, two parts. The first part, these four elements, these basically deal with the data set. This one that I put together.
You still need to share your screen. Please share your screen first.
Oh, just a minute. Okay, do you have it now?
Yes, we can see. Can you make it full screen?
Just a minute. Okay, as I said, my this will be in two parts. This data set is now archived for access to all, and I thought it would be useful to spend the first part of this talk simply describing some of the things I've done with that data set. It's by no means a perfect data set, so I just want to make a few comments on that. And then some of the things I've done with this data set, and also with data that I've recently incorporated from looking at stations on the ice. They are not part of this data set, but they are part of some work that has been a follow-up. So first of all, we'll take a look at the location of Peyto Glacier. It's basically a mid-latitude glacier in the Western Cordillera of North America. And I think these maps show it pretty well. The thing about the Western Cordillera, you have the coast mountains, the Rocky Mountains, in which Peyto Glacier is located. This is largely a continental type of climate. This very strongly maritime. And so we have more precipitation in the coast mountains, sometimes up to 2,000 millimeters per year. In the Rockies, it might be about half that much. And so equilibrium line altitudes tend to be higher in the Rockies than they are in the coast mountains. If we now go to the base camp itself, or the station location itself, this is basically the weather station in 2003, more than 10 years after it was first put in. And at that point, it had pretty much the full suite of measurements. Total precipitation, very important for modeling. 2 measurements of incoming solar radiation, incoming long wave radiation, 2 measurements of air temperature, ground temperature. Later on, we added pressure, air pressure, and of course, wind speed and wind direction. And looking at this slide, you are looking straight into the face of the prevailing wind. It's a prevailing south-southwesterly wind. It's an orographic regional flow regime, which means that air comes over the mountains and down into the basin. There are also surface katabatic winds to think about. And because of both of those things, considerable adiabatic heating, I think, of the flow down through the basin. Turning to the data set itself, it's not a continuous data set. A few of these are because of failures of instrumentation, data loggers, and so on. But for modeling purposes, you need continuous data sets. And of all the data collected there, 6 were selected as being essential. Incoming long wave incoming shortwave radiation, incoming long wave radiation, air temperature, relative humidity, wind speed, and precipitation. Now these ones I've highlighted in blue. Various ways were found to fill in gaps in the data. These could be anything from interpolation to the use of reanalysis data. Fortunately, it was kept down to a small amount. Now, for users of this data set, they should pay particular attention to the flagging system. We have a flag here which says the source flag. Flag 1 means the source is the main station at Peyto Glacier. Number 2 means it's sourced from the ice surface itself, because we didn't have the main station available. And then if all else fails, we go to reanalysis data. Now, to qualify as a 1, at least one member of that data set has to be from the main station. That means that substitutes could be found if the others, some parts of the others were missing. So in fact, in this one might find, let's see if we can take this down a bit. We might find reanalysis data showing up in main station data. But if we look at what we've actually had, 2.8% of the file is exclusively reanalysis data. If you look at each individual element, that rises a little bit to 2.9% for the incoming radiation. The big one here is incoming long wave radiation, and that because a sensor wasn't installed until about 10 years after the station started. And then a number of things had to be done to that to make it work. And then air temperature, only 3% of that is reanalysis data. Relative humidity data is a little bit higher at 5.1%, and then wind speed, 3.8% of it. I won't go into too many details of these things because you can read about them in a cover paper that I have made or that I've written. It's a fairly free-form type of document, but it could tell you what's in the data set and how much you might want to trust certain elements of it. Basically, the vast majority of it is based in the basin. And that means it's a good source for modeling with real data. It's also a good source for calibration of reanalysis data. And you know you have a good one when it's a 1 and a 0. 1 followed by a 0 in any one of these fields means that any one of these fields is a good set of data to use for calibration of reanalysis data. I want to take a few examples of some things I've done with these. Not all people would approve maybe of some of the things I've done, but when we installed a new sensor for incoming long wave radiation, we found we had a noise problem in the signal such that the signal might be suppressed for part of the day. Fortunately, we did have the old sensor going. And although the old sensor had been modified for use with Landsat work, we could use that to boost the signal if need be. And there the trick was simply to take the this gap and adjust it to patch it over so that we had then as close as we could get to a very good signal. And there was no problem with the two radiometers in the sense that when the this one wasn't being affected by an occulting wedge that we'd installed, the two agree very well. A little more problematic is the incoming long wave sensor, which it's an old style, it's an Epley incoming radiometer, which uses a battery compensation circuit. The batteries in this thing never seem to work for very long, very well. So we had to resort to, or I had to resort to using air temperature as a way to estimate what the cavity temperature of the Epley was and substitute that. Now, if I compare that to where the, when we had a battery with the estimate, we find it's a little problematic on an hourly basis. For instance, there are times when there's some fairly sizable deviations, but over the long term, it looks like a pretty good substitution. So this is what I would call an excellent adjustment to the data. This is probably pretty good. Of more concern might be what I did with the relative humidity. We'd started with an old humidity sensor, which at first performed quite well, comparable to the one that replaced it eventually, which is a Visalis sensor. See, this is 88, 2003. Right after that, we became aware that this signal was decaying. It just wasn't sensitive enough. And my first thought on looking at that was simply to get rid of it and perhaps use reanalysis data. But then I noticed that it seemed to be progressing each year, almost in a linear fashion. So I put a linear correction into it. And by adjusting it that way, I was able to bring it back up to the level that it should be. Now, if you compare this trace here with the 207 sensor, and you compare it to the Visalis afterwards, they look pretty much the same. So perhaps not too much was lost to that, except when you take the difference between these two to get the vapor pressure deficit, you find that, yes, there are times when there's an overranging of the relative humidity, as though the sensor came back to life from time to time. So I had to place a limit of 100% on the 207 data. That is one. If people are using the data set, they might want to give some second thought to that. I thought it was valuable to keep it, so I kept it. But you'll see that's the whole purpose of the flagging system, was to alert people to that. Data from the ice surface. Sometimes when the main station didn't work, we had the station on the ice that could substitute for it. And the station on the ice is just within 1 kilometer from the base camp and at about the same elevation. So it was possible to compare sensors, for instance, incoming radiation, virtually the same signal. So just took those when we had to as substitutes. Air temperature was a little bit more of a problem because although the two agree pretty nicely in cold weather, when you move to temperatures above zero, there is a distinct glacier cooling effect in the air. So that meant that any temperatures from the ice had to be adjusted by a cooling correction factor. In other words, multiplied by about 1.1. And there were 2 times when this, in the record where this had to be done. At that time, also had to apply an intercept and a slope correction. But these make very good substitutes. Relative humidity, a straight regression showed a need to adjust the signal for the regression parameters. And a check back against what type of vapor pressure you obtain from that showed that you get a very good agreement between the substituted vapor pressure or the vapor pressure from the relative humidity substitutions and the vapor pressure at the base camp. Wind speed. This was a problem because I could not come up with a consistent relationship or rule because the wind pattern breaks into 2 regimes. You have this cluster of points here and this cluster of points here. And I see them in both cold weather and warm weather. In other words, both winter and summer. And at that point, there was no adjustment made except simply to use wind speeds on the ice as substitutes. Because I couldn't come up with any better rule than that. Reanalysis data. There are 2 major periods where these were used. One was shortly after the station had been installed, when the recording equipment was not yet ready for cold weather, about a 6-month period there. And then another period in much of 2009, when we were missing over 6 months of data there because the battery at the station had failed. So this is, sorry, not that case. When the battery at the station failed, if I can go back to this slide, that is when the ice station was working quite well. So we used those values. But early on, we had to make extensive use of the reanalysis data. And of course, we have the reanalysis data that have been bias corrected. And I used those, but I checked them again against a series that I had from 2003 to 2006, where all things were working in the main station quite well. And found that I really didn't have to make any adjustments. So what I did here was to decide if I needed to make an offset or a gain adjustment to the bias corrected data. In the case of incoming radiation, I didn't have to do that. In the case of air temperature, just an offset correction. In the case of wind speed, I did this by simply reducing the mean bias error and using a multiplier of 1.34. For the offset and gain adjustments on the long wave, this is where I had the biggest changes. And so these were applied to adjust the signal. And I'll have a bit more to say about that just in a minute. But doing this, I find that the bias in these, which is on this scale, is small compared to the size of the signals that we're looking at. And here I've only chosen 3 elements to look at, but it gives you an idea of what was done. There are also short-term reanalysis segments, ones where they were too long for interpolation and well, too long for interpolation, but short enough that differences between the reanalysis data and measurements would show up as step changes in the signals. So in cases like that, usually periods of 6 days or less, in fact, most cases, parts of the day, there was simply a adjustment, a step adjustment made to bring this segment back into line with the rest of it. After all that, the question is, how does that compare with the station that replaces basically this station that I'd installed in '87? Here's the station, and here's the one installed by the University of Saskatchewan. We've referred to this now as the main station at Peyto. This one is the old main station. And so do the comparisons, this one with this one, both measured at the same height. Incoming long wave with incoming long wave, temperature, and so on. And in the case of temperature, radiation and relative humidity, excellent comparison in the first year of these comparisons. I just did them for the first year because I want to see what I was handing off. The comparison, not so good for wind speed. I'm not too concerned about this comparison because the correlation is very high. And I think you could attribute that to the fact of this being cited here, this one being cited up here. There's probably some difference in exposure that accounts for that. More problematic is this one, which tells you quite a substantial slope for the relationship. And it tells me, I think, that perhaps I might have over-adjusted. Perhaps I should have accepted the reanalysis data as they were. In fact, if you take the inverse of this, you get about the same multiplier that I used in the, in the previous slide to make the adjustment. So my advice on this, the whole data set is recalibrated according to the way I did it. I think if I were modeling, in fact, I've done this already, I would probably adjust the long wave radiation in my data set to agree with the long wave radiation measured at the new station. And reason for that, you're basically comparing an old design sensor when you're doing this with a modern design sensor. And my bias is to give a little bit more credence to something that's new and maybe better designed than old sensors were. Now, precipitation. I pointed out that this was a problem, and indeed, I found if I used a non-standard filtering technique, I could get pretty good seasonal totals of precipitation. Trouble is, if you look at these, they're very smooth compared with actual measurements. One's taken at Bow Summit, Golden Airport, and the ERA data. So I've figured there's simply no expression in this filtered signal. And what I've done in the filtering is basically to lose hourly and daily detail. So figure the best option, use the ERA interim and Golden Airport data in my my work. The model itself, using these data sets, so these are the data sets over 30 years, incoming long wave and short wave radiation, air temperature, and vapor pressure derived from the relative humidity. Wind speed, I've put wind direction in here just to give an idea of the prevailing wind direction. And then precipitation amounts. Now, I was quite interested in Golden, even though it's 50 kilometers away from Peyto. Peyto, of course, is only 5 kilometers from Bow, because I wanted to see what a actual set of measurements would do in the modeling procedure. If I look at what I've done, well, it's a standard type of raster modeling approach. The 25-meter resolution, there are over 27 or 37,000 points in the raster. I'm using a regional precipitation gradient of about over 0.1% per meter, a 1.5 degree temperature threshold for rain and snow, topographic adjustments for radiation, katabatic regional turbulent flux scheme without glacier microclimate. And I have standard temperature and pressure lapse rates. It takes about 5 hours to do a 30-year simulation, at least in my computer. Others may have faster computers. And what I get out of that is quite interesting for me. I can do things like snow line extent or snow distribution. So if we go here from late winter of 1 year into the spring, from the accumulation season into the depletion season, what we see is the tongue disappearing from view as the snow melts away. It continues on through the summer as the snow line gets higher and higher. And then at the end of the summer, which is actually the end of the previous mass balance year, the new mass balance year starts up, and we start to see the tongue reappear again, exposed by the snow cover. It makes a pretty good simulation of annual mass balance. Now, I'll simply to point out what I'm doing here, begin the new mass balance year. Each one of these traces is a mass balance year. So there's the beginning, goes up to the height of the winter mass balance, where people take winter mass balance measurements, and then down through the ablation season to the end of the mass balance year. So we have 30 of those things across the screen. I get pretty good points of agreement, at least, excuse me, at least 7 years during the simulation. But the winter mass balance values are only about half of what field measurements say. And at first I didn't spot this because there were the World Glacier Monitoring Service, there's a 20-year gap in that sequence, but I could catch this sort of out of the corner of my eye. And I thought, well, I'd like to explore a little bit further. And the only way to do that is by going onto the ice itself. So if I go onto the ice, find 3 stations, the tongue, which is the longest history, it goes back to 1996, middle portion of the glacier, and the high portion right at the saddle with Peyto Glacier. These are about 200 meters apart in elevation, so good range. We have wind speed, temperature, relative humidity. At the lower station, even incoming and outgoing solar radiation, and SR50 measurements, sonic sounder measurements of the surface. Now, these stations are extraordinarily difficult to maintain on a year-round basis, as we discovered. We tried early. Geological Survey of Canada tried one at high elevation. It lasted for a year. Kept on trying with ones at the middle station. Sometimes they worked, other times not. And this picture was taken 2007. I didn't see it the next year when I came back. Where did it go? Well, we found it 2 years later. Apparently it had been blown over, and eventually we found the legs sticking up out of the snow. So tried to install it again. It fell down again. My last attempt to install it was in 2011, thinking, well, I'll never see that one again. But fortunately, it lasted. And in fact, we get a 3-year comparison of or sorry, a 2-year comparison of all 3 stations at different elevations. And there's a lot that you can do with that kind of information. One of the things you can do is to take a look at the distribution of the temperatures and the vapor pressures across the stations. I took a look at, first of all, lapse rates, very high lapse rates, very close to adiabatic, and higher than you'll see mostly reported for lapse rates, but not unheard of. I've seen some of these, I think for one study in the Langtang Basin and also in the Italian Alps. It's slightly lower in the summer, slightly higher in the winter, and that's pretty consistent with what you see of studies of this type. Most remarkably, I could use a single cooling factor, and this is now the reverse of what I'd shown you in going from ice to base camp or main station. We're now going from main station to ice. And by using this one lapse rate and the cooling factor, I was able to come up with estimated ice temperatures that agreed with the station temperatures fairly well. So those are, very good comparisons. That actually surprises me because I would have expected some progression. I mean, that's been reported for Place Glacier and other small glaciers, but this one seems to hold up, possibly because of adiabatic damping of the cooling effect. The other thing is that I found that a linear lapse in or increase in relative humidity could be projected out to the glacier surface and then applied against the saturation vapor pressure at the ice temperature estimate, be used to make pretty good estimate of the vapor pressures across the glacier surface. Not as good as for the temperatures, obviously, but still pretty good. The big problem for me was wind speed. Again, the same breakdown into apparently different wind regimes. And what I think I see here is the katabatic the katabatic signature in the glacier boundary layer showing up when the regional wind is light. It's always there, I'm sure. And it causes me to think that basically the katabatic or the glacier boundary layers is a mixture of katabatic winds and regional winds. And the katabatic layer sort of oscillates in height like this. And how do you prove that, or how do you find out something about that? Well, in 2008, we set up an experiment where we had a fixed eddy correlation system set about 2 meters above the ice to compare with a mobile system. And so this was compared with measurements at 2 meters, 4, 6, 1, and so on. And the results are here, which I think is pretty hard to see. So let's just move to an expanded version of that. And what I see here, these lines, I'm highlighting places where the mobile sensor is measuring noticeably less sensible heat flux than the fixed sensor at these points. And these are points where the mobile sensor is quite high above the ice, 5 meters, 6 meters, 4 meters. The other thing I'm saying is that if you look at the bulk transfer estimates of those, accepting eddy correlation values as true values of the fluxes, the 1 meter estimates agree very well with the fixed values. The 4 meters provide by far the highest values, and they overestimate values by quite a bit. So one conclusion from this, keep the bulk transfer measurements, if you're doing those on a glacier, as close to the glacier surface as possible. The other point is the katabatic wind is basically a quasi-stationary feature of the glacier boundary layer, which to say it has a now you see it, now you don't aspect to it. It's not such a steady feature. It's there under the right conditions, but every now and then it will collapse. I take this now together with the micromet work, and again, taking eddy correlation measurements of sensible heat flux, these little dots in here, and latent heat flux down here, I see that these agree pretty well with bulk transfer estimates. And that tells me that if you can model the glacier microclimate from the base camp station and apply a bulk transfer approach to it, you might have a viable, you would have a viable modeling scheme. The other thing of interest, just how much the net shortwave signal takes up of the total melt at the glacier surface. So it looks dominant. And in fact, when I compare the SR50 measurements with water equivalents of radiation, something I call GRIM, and I won't go into the acronym at the moment, but basically net shortwave or incoming shortwave radiation converted into long wave, or sorry, converted into net shortwave radiation using the surface albedo, and height equivalent by using the by applying the density of the snowpack, and doing that cumulatively, you get very good fit over the ablation part of the SR50 signal. If you take precipitation at Bow Summit this time and increase the elevation gradient that I'd use by double, you get pretty good fit to the accumulation parts of the cycle. And that's really pretty exciting to see. The other thing I found really exciting was to use the Harder and Pomeroy rainfall fraction. In this case, using the wet bulb temperature to work out what the fraction of rain over snow would be. And that produces some interesting results. Not too surprisingly, rain seems to be most featured at low elevation, snow at high elevation. You can even look at times when rain most occurs, which of course summer, but early indications that there might be rain on snow, and wonder if this explains ice layers in the snowpack. Of course, when you look at you put this together with actual precipitation values, you find it wasn't rain on snow, so perhaps it was a melt layer on a sunny day. Putting all this together, I've now got a new simulation. At first, I tried using only net shortwave radiation because I was quite excited by that. But basically, all the annual mass balance results were down in this area someplace off the graph. I found that if I used the full energy balance, it was better, but still not in this range. And then, but I had noticed that by increasing to 0.26% per meter, my winter mass balance values had gone up. So what if I just arbitrarily increase to 0.39%? Well, when I did that, the winter mass balance results were right there where the measurements were, and the annual mass balance results were now back in the range. I found that the best decade of simulation was the second decade, which in fact was the decade when the digital elevation model had been acquired. So a couple of questions I have from this. I'm not happy with this so much because this is no longer a measured parameter. It's basically a tuning parameter at this stage because it's the value that makes the model fit best. What I'd like to see by way of going further, first of all, a digital elevation model that changes from one year to the next to keep up with the changing appearance of the glacier. But further work considered, besides that, this is the one I mentioned here, explore the effects of a variable precipitation gradient on these results, because I think everybody has trouble reconciling annual mass balance with simulations. This is all a fixed precipitation gradient. What if that were to change from year to year? And of course, on what basis would you estimate that change? So looking back over it, if I sum up the successes of what I've been doing so far, successes, well, these are successes, you know, the pretty good job of simulating the or of estimating the glacier temperature and humidity fields. Here, I'm still stuck. This is not an estimate here. It's still the base camp value. And the best I could do is say, well, about 2/3 of base camp might give you an estimate of wind speed on the glacier. So that poses an interesting problem. How does one construct an all-season procedure for replacing the base wind speed with an ice wind speed estimate? At this stage, I don't know. And it's not an easy problem because this shows up in the winter as well as the summer. Now, we're used to the idea in the summer, just take the air temperature above 0 degrees C and you can model something from it. Certainly success in confirming the dominance of net shortwave radiation and ablation due to snow and ice melt. But I mean, I've known that since the times when I was doing my doctoral work. An important problem that comes out of this, how does one obtain a better picture of the precipitation gradient from the glacier AWS data? And I don't know what to do except to try to explore the winter signal, as chaotic as it may be, and see if there's some kind of a filtering procedure which might give a better picture of that, such that we might start to look at event by event snowfalls and see if there's any change there. Work in progress. Well, as we can see from this comparison of model to SR50 data, still some work needed if we're to get on track. This is probably the best of the comparisons. This is not so good on the accumulation part. The ablation part is pretty good here, pretty good on accumulation, but something happened in here, and although the slope is right, it's way out here somewhere. So if I could conclude with that and simply end with a picture that I took one morning as I was about to walk out on the glacier to look after my Met stations and explore the basin. It's a scene of immense beauty, deep mystery, and I just hope I've been able to share a little bit of my exploration of at least one aspect of its mysteries with you this evening.
So
You're done?
Yes, perhaps I should have said at the end.
yeah, thank you very much, Scott, for your very, very comprehensive, long history of mass balance story in Peyto Glacier of Canada. This kind of study is very rare in case of Nepal. So there might be a few questions for you. I can see one. I want to open the this floor for the questions. So if there is questions, and then you can come forward and ask directly. I can see one question in the chat box by Amrit Thapa. So Amrit, can you ask these questions directly?
Let's see, I can't see everybody in that. Wait a minute.
Yeah, hello, can you hear me?
Yep, I can hear you. I'm just trying to see you.
I have some issue with my internet, so I have turned off my video. Is that okay with you, Professor?
Wow. I just wish I could see everybody right now.
Yeah.
Yeah, please go ahead.
Yeah. So, Professor, in your comparison of meteorological observation with ERA, so you use ERA and TRIM, and I was very curious to know about why didn't you choose the latest version of ERA product, that is ERA and ERA 5 land, and then go for ERA and TRIM? Is it because you did that analysis long time back, or you have some other specific reasons of using ERA and TRIM? That is my...
Okay, that's not something I'm familiar with.
So yeah, so you have used ERA and TRIM to make comparison with station observation, and also use it for filling some of the missing observation, right?
Yes.
And
What I've
then,
done,
yeah,
yeah, well, what I've done here is simply station to station comparisons. The stations were values were plotted at altitude, so I could work out gradients. If that's, if I understand your question correctly.
yeah. Thanks, Professor. I might have misunderstood something. So you showed comparison of ERA and TRIM with the station observation in one of your slide, and I was
Yeah,
curious
does this
why.
have to do with the digital elevation model itself?
Yeah,
Is this
yeah,
what the question relates to?
yeah.
Because the model is, sorry, okay. The model was derived from LiDAR imagery.
Yeah, thank you.
Yeah, thank you, Professor, and thank you, Amrit, for your questions. And if we have a couple of more minutes, if you have any question, please come forward and ask directly to Professor Scott. He might be happy to get your question.
Can I?
Yeah, Suresh sir, yeah, please.
Okay. It was overwhelming, to listen to you with your lifetime's work. This is something which we dreamed here in Nepal in the 70s to begin when we started meteorology in the university. And we did some work with in collaboration with our Japanese colleagues. My name is Suresh. I understand we have a common friend, Gordon Young. Gordon Young is a very close friend of mine when I was involved in snow and ice studies and research. My name is Suresh Chalise. So it was a kind of, dream come true through your work, because, after all, science is universal, and we can see your methods, and I'm sure most of our young researchers will be very much inspired by your by your work. I have absolutely no reservation to say this is one of the most overwhelming and astounding work, and your dedication when I see throughout the year how you really stuck to it. I could not. I could not. I left after some time the field, and there were some pressing reasons. But it is a very inspiring talk. I'm very happy he has invited to participate in this talk. Thank you. Thank you. And I'm sure most of the deputy students will be again calling you or writing to you, or on several issues. So I don't want to take more time, but my heartfelt thanks to you for taking this time to present your work to us. Thank you very much.
Well, thank you for those kind words. In fact, Gordon Young and I were both doing our doctoral work at the same time on Peyto Glacier. Gordon is the very first person I walked into Peyto Basin with, and many years later, the last time I ever walked out of Peyto Basin was with Gordon Young. So we've been quite close over the years. If I could address as a question, I just pulled up the chat. I might have misunderstood the question that I had earlier. This had to do with the reanalysis data, I believe. Why I would use the ERA interim rather than ERA 5.
Yeah, I think so. Yeah, he was asking about
Yeah,
like
and
why.
I know this came up in the commentary on the ESSD paper that we did. One of the reviewers had asked that question, and of course the ERA 5 has better resolution than the ERA interim. I simply used it because it was available. I mean, I know there are others out there for the Saskatchewan glacier right now. That's right now a cryosphere discussion paper, and they've actually used the North American reanalysis data. These, I think one of the, I simply used it because it was available and easy to get at. Excuse me. And immediately easy to get at. By all means, if there are other platforms, I know there's several reanalysis products out there, each of which can be tested, I think, against the data set that is now posted, which is of course one of the main reasons for posting that. You won't find too many 30-year data sets of that type that you could use to calibrate reanalysis data to see, whether it's North American reanalysis, ERA interim, or some other reanalysis set. But with that data set and looking carefully at the flags that I put into the system, you'll be able to, you have a good resource there where now you can look at these products and see which one best suits your needs.
Thank you, Professor Suresh and Professor Scott, for your nice conversation. Also, the nice appreciation by the Professor Suresh about his contribution in the research in Nepal in the long time back. So, if there are some more questions, we can take one or two more questions. Then we can go for the another session. If there is any question, you can raise your hand or you can practically come forward and ask your question.
Can I ask?
Yes, please go ahead.
Hello, Professor. It's very nice and comprehensive presentation. So my particular question is, I'm also doing similar kind of work here in Nepal based on two automatic weather station, which is installed on glacier in Nepal, Glacier 2 glacier. But while calculating the mass balance based on the energy balance that is calculated from the automatic weather station that is on glacier automatic station, it exactly matches with the mass balance stick nearby the AWSs. But while I was trying to extrapolate the mass balance over the glacier to calculate the glacier-wide mass balance, I didn't get such a pretty nice model result with the observed one, because I have used different kind of albedo model. So in your calculation, I can see that the albedo, I think you also used a different albedo model. So what is your suggestion for us to use, or which or what is your suggestion to use for using different kind of albedo model, or is there any other reason that I get for getting different kind of extrapolating, I mean the result for while extrapolating the mass balance based on the AWS data? So.
Okay, when I set up that model, the first thing is to assign an albedo to particular surfaces like rock, ice, and vegetation, if there's any in the basin. I mean, it's a whole basin model. Snow albedo is modeled according to snow thickness. And what I did there was follow some of the Utrecht University work. I think that was Knapp's work, Wouter Knapp, K-N-A-P-P. If you look him up and look what he's done with albedo modeling, that's basically the modeling I used for the snowpack. And it seems to work reasonably well. But that's the only dynamic part of the albedo model. I mean, the others are, background surfaces. The albedo will change with snow thickness, and that's what Knapp's model does. I can't run the details off the top of my head, but so it is a changing albedo model. Now I don't know if you have incoming and outgoing shortwave radiation measurements.
Yeah, I do have all four kind of radiation components. So based on the incoming and outgoing sort of radiation, I calculated the albedo, and then based on those four component radiation and then calculating the turbulent heat fluxes, I calculated the mass balance, and it exactly matches with the stake nearby it. But while extrapolating, it didn't match. I used different albedo model for that case. So that was my issue. So I mean, I'm not sure why the albedo model was not working well in my case.
Okay, well, one thing we have to be careful with measured albedos, I think most people are finding it's best to take the daily total of incoming radiation and daily total of outgoing, and then use that ratio to work out what the surface albedo would be, because these things can change. Small changes near sunrise and sunset can cause some odd values. The other thing you're using, what are you using for turbulent transfer?
Tika?
Sorry, what are you using for turbulent transfer? How are you calculating that?
So I'm using the simple bulk aerodynamic methods to calculate So where I use the wind speed, yes, and the relative humidities, air temperature.
Mm-hmm. How high are your sensors above the ice?
When I installed in 2018, it was exactly 2 meters above the surface. but it was on the station was on glacier, so it is changing time to time because of the albedo. I mean, the surface height was changing.
Yeah, I know that's a frustrating thing to deal with, the changing glacier surface. What we've done, or what I've done, the automatic weather stations, we would drill them in at some locations. At the lower location, we actually drilled in the legs at angles, and then let it melt out over the summer, and then re-drill it again at the end of the summer at that station. At upper stations, we drill vertical stakes and then just simply attach the base of the tripod to those, and then hope that we could readjust it before too much change had occurred. When you're dealing with bulk transfer, you can use your measurements above the surface to tell you what your instrument height is at any one time. I would presume you have a sonic sensor on the station.
Yes, we do have.
Yeah.
SR50.
Yeah, and then if you know the height of your instruments in relation to that, you can always keep an ongoing account. Now, I don't know if I can get back to my presentation slides at the moment. Simply go back to another something I can show you about. Okay, if I go back to oh.
Anyway, if you
Okay, can you,
okay,
yeah.
okay.
Can you see my screen right now
Yes, it is.
for my presentation? I just want to go back to show something about, because as time is getting on, I didn't stay as long on some points as I wanted to. Yeah, if we go back to, yes, this one here. These values. Looking at some work that I think it was did with Shea on the Yala and the Mara glaciers, and looking at sensible heat fluxes actually for glaciers in high mountain Asia. One thing to check is what your values look like. Now, you would probably be getting values something like this, like what I got out of the automatic weather station. And this is what the Eddy correlation gives you. These values are higher, and this value is higher. Why is this higher? Well, because these measurements apply to heights greater than 1 meter above the surface. In fact, these are probably 3 to 4 meters above the surface. That's when you can start to get fairly large overestimates of the heat fluxes from bulk transfer methods. This one here is higher simply because my wet bulb wasn't wet enough, so to speak. It just didn't cool down enough. But these kinds of values are pretty good. If you look at this ranking, it's pretty much what you see for glaciers. Very strong net shortwave component. The long wave component is persistently negative. I know during monsoon periods in Nepal, it can approach zero or maybe even be a bit positive. After that come the sensible heat and the latent heat fluxes. And what happens in high mountain environments such as you have, these values go down because while the air is thinner, it's colder at higher altitudes, and this value even becomes more persistently negative. And that's simply the altitude factor in those glaciers.
Thank you, Professor.
So I don't know if I've answered your question very well, but the person I would look up on albedo is Vutra Knapp. So that's Knapp. And these days I'm finding that if I use a search engine and just type somebody's name in with a topic associated with them, you can quite often turn up a relevant paper that's very helpful.
Sure, thank you, Professor, for suggestion.
Yeah, I think with that question, I think we may end the question answer session as the time is passing. So next, we are going to have a short remarks from the Professor Dr. Rijan Bhaktakaista, who is currently representative from the International Association of Hydrological Sciences Nepal chapter, also Associate Professor of Kathmandu University. So could you please put your remarks? Listen, sir.
Okay. Can you hear me?
Yeah.
Yes.
Yeah.
Okay. Okay. Thank you very much for the organizers. And we have seen here 4 or 5 organizers, mainly the Glaciology Society of Nepal, IHS chapter, which I belongs, and the Small Earth Nepal SEN, and the next one is also from my Kathmandu University, Himalayan Cryosphere Climate and Disaster Research Center. Next, we have Central Department of Hydrology and Meteorology, Tribhuvan University, and also the UNESCO. So here among 6, I belongs to 2, and I would like to thank the other 4 participants, the organizers, co-organizers of this event on this Nepal's National Water and Weather Week 2022. I think we have learned much from Professor Scott Munro's presentations, which is very nice, and there are lots of informations. And after hearing Professor Scott Munro's presentations, I also thought that we also started such things in 2012 when we have one project called this Cryosphere Monitoring Project, supported by the Norwegian government through the ICIMOD. And we have started that project from 2011. And in 2012, we have installed stations like this, automatic weather stations. On the, this is Yala Glacier on the backside, Yala Glacier in Langtang Valley. I think you also mentioned this. And this is a pluviometer, precipitation gauge. And this is on the Morin site, we can say, Morin site. And we also installed the one station on the glacier, like this. This we call as a mobile AWS. But as you said, we couldn't put it for a longer period. It's just for a few months, I think. And then it was very difficult to maintain. And due to some harsh weather conditions during that time, it fell down. Then we couldn't continue the measurement on glacier site. But this previous one, this on the Morin site was still there, I think. Yes, still we have this on Yala Glacier Base Camp. So we have also started, and as you have said that, I think the comparison of on glacier and off glacier are very important. And before that also, when I was studying the Doctor of Science, Ph.D. degree in Nagoya University, Japan, we went to this Khumbu Glacier in Everest Base Camp area. And then we observed some the meteorological features on glacier and off glacier. And then we found that, as you said, there are totally different natures or features of snow ice melt as well as meteorological conditions. On the bare ice, we will have a very low air temperature, and on the debris covered, it will be very high on debris. very high, but on moraine, it will be the maximum here. So these studies are very important, but this was only for the about 11 days. So we can see here the 11 days. Total, we stayed about 2 weeks on the base camp at the time. This was done in 1999. We measured after installing all the stations equipments. So we measured these parameters from 22 May to 1 June in 1999. And then we also compared this surface temperature also, debris covered as well as on the air. So in case of air, it is lower, but on the debris covered, it is very high due to the incoming absorption of incoming sort of radiations, because albedo is very low on those cysts, I think, it's the nature of the rock. So these were also carried out, but the problem is we couldn't continue for the longer time periods. That is the main problem in the Nepal Himalayas. And recently we have started such studies on Peyto Glacier in Manang. There also we have installed one AWS on the glacier side and next on the moraine. And we have started the measuring these meteorological parameters from 2015 November, but from 2016 we have the data, and still the stations are there, but due to this COVID-19 pandemic, we couldn't go there for 2 years, and now maybe after 2 weeks we are going to there on Peyto Glacier and retrieve the data. So these are the some our experiment or the field study revisions, and which from those your presentations, we found that the field data are very necessary for reanalysis data adjustment or the bias corrections, because you have already used those field data to correct this ERA interim data. So therefore, we can say that field data are very precious, and as far as possible, it's better to continue such field experiments. And the next one is, I have seen that you also mentioned that wind speed measured at 2 levels on the glacier side. So that may be due to this roughness parameter also, because we can get roughness parameter if we have 2, 3 wind speed at different levels. And also you mentioned that since your wind speeds, the wind speed sensor, wind vents are little higher, more than 2 meters. So we found higher energy balance components. So I think due to that also, so these are the few notes which I got from your presentations, which is very good. And I think for the other young researchers also, it will be very useful to continue such studies in the Himalayas also. Although we started in 2099 from when I was in Japan, it didn't continue for much. And the Japanese researchers also studied on this Trakarding and Rikasam Trakarding and Trambau Glacier in Dolkha. There also, I think they don't have such detailed informations. So I think we need to have such experiments on the field for the longer time periods. So with this few comments, I would like to thank Scott Munro for your very nice and comprehensive presentations. Thank you. Back to Mohan.
Yeah, thank you, Rijan sir, for your nice and overview of the research in Nepal. Also, we would like to congratulate you for being promoted as a professor, if we heard rightly.
Yes, just today it was announced. Okay, thank you.
Yeah, and then next we have remarks from the Professor Dr. Deepak Aryal, who is a professor and the head of department at Central Department of Hydrology and Meteorology at Tribhuvan University. Professor Deepak Aryal, sir, could you?
I'm here.
Yeah,
good
okay,
evening,
please.
Good evening, and maybe for Scott, it's morning. Can you see something in the slide? Oh, no.
Yes, I see. I think I see the ascent of Everest.
Yeah.
One of these.
Yeah, actually, I don't have that much comments and that much suggestions, but what I would like to say is,
Yeah, if you could,
I
if you
have
could.
been only
Yeah.
few things I would like to tell. One is,
Mr. Deepak Aryal, would you like to
Yeah.
make it full screen?
yeah,
Yeah,
I
if you
will
make it
try
full
this. I
screen,
will
that'll
try
help.
this. Is that okay?
This is Word file. Maybe it's difficult to make a yeah.
Let me try my
No,
own.
okay,
best.
okay. Without this, I will go without this.
I,
Without this, I
well,
have.
I can see the slide, but now I did something and I lost it. Let's see.
Okay, okay. Without this, I'll go without any slides. So Dr. Scott Munro, who served as a professor in geography, he did his PhD in 1975 when I was 6. I spent all his life working on the glacier and working on the AWS things. So I think I'm not able to comment on his study, and I'm not that much eligible to give some feedback on his study. But even then, I'm very much impressed with his work in such a hard areas, not that easy to go in cold regions, even in Nepal as well as in any part of the globe. So he has such an experience. Recently, we have installed some more stations in Nepal. Maybe probably Dr. Scott know about these things. In the Everest region, as well as in the southern part of the Everest region, we do have some mass bands in more than 4,000 meters to up to 8,000 something meters. So these data, and if somebody those here, we have some students, some researchers also attending this webinar. So if they or some of them collaborate with you and our department, as well as Nepalese Glaciological Society, IAAS, some collaborate with you for the study matter, because now due to COVID pandemic, we are very close due to these webinars. So we can get some more and more extra results from Nepalese data also. I think this will be, we will be much beneficial, so that you have each segment's data, very tiny information about AWS things. And you did a lot of comparisons with reanalysis and some other models data. So that's why what I like to suggest youngers, they should be in touch with you, and we should be in touch with you, and we should have to use our own our region's data, I mean that Nepalese Himalayas data, so that we can make some special research work in this field. With this, I would like to thank you and congratulate Scott for your nice presentation, as well as reason for being a professor from today. Thank you very much.
Well, thank you so much for your kind words, and it's as I said, it's been such a pleasure to talk with with all of you today.
Yeah, thank you, Deepak sir, for motivating us and other younger generation. So we are almost at the end of today's webinar, and then lastly, I would like to request Miss Prakriti Gurung from UNESCO Nepal. She's on the behalf of the Michael Propt, she's giving her closing remarks of this webinar. So I would like to request Ms. Prakriti Gurung for closing remarks.
Hello, everyone. Can you hear me?
Yes, we can hear you.
Okay.
Yes.
Can you see me as well? I've turned on my video.
Yeah.
Okay.
No
All right. Great. So good morning and good evening, everyone. To start with, Mr. Michael Frost sends his sincere apologies for not being here to give his closing remarks as initially planned. He was really looking forward to it, but due to some unforeseen circumstances, in the last minute, he just could not make it for the webinar. And I'm not as eloquent of a speaker as Mr. Croft, but I'm honored to be here today on behalf of UNESCO, and would like to first thank Professor Munro for your wonderful and highly comprehensive presentation. As all of you may quickly pick up, I'm not an expert on either hydrology or glaciology. However, living in Nepal and anywhere else really, it has now become impossible not to have an interest or conversation around these important topics. And in fact, the upcoming country strategy of UNESCO prioritizes research and discussions around mountains in Nepal. And one of our 3 priority areas in science has been aptly termed from cryosphere to biosphere. While ICIMOD has been identified as a key partner under this priority area, the office has been fortunate to be associated with experts such as Dr. Dheeraj Pradhananga and Dr. Mohan Chand in the past. In fact, the science unit in UNESCO Kathmandu office had been inactive for several years. And the first event we organized in the office in science was on International Mountains Day last year. And it was on December 3rd or 8th. I'm sorry, I don't remember the exact date, but we had an event on December under the theme Tribute to Glaciers with Dr. Chand in the panel and Dr. Pradhananga as the moderator. At the UNESCO office, we are committed to promote sustainable mountain development. And to this end, we are extremely interested in collaborating with the government, with NGOs, universities, and youth groups, amongst others. We truly value your expertise on the field and would like to support your effort in any way we can. At UNESCO, we believe having regular webinars, events, and discussions around important topics such as glaciology, hydrology, and impacts of climate change in general is essential. And we would like to thank the Glaciology Society of Nepal, Small Earth Nepal, Himalayan Cryosphere Climate and Disaster Research Center from Kathmandu University, IAHS Nepal chapter, and the Central Department of Hydrology and Meteorology from Tribhuvan University for inviting UNESCO to be a part of this webinar. More importantly, thank you, Professor Munro, for taking your time to share your experience and knowledge with us today. It has truly been a pleasure and honor for me to be here and to listen to you. And as evident from the engaging discussion, I believe the other participants present here feel the same. With that, I would like to thank you all and end my remark tonight. Good night and good morning, everyone. A very happy World Water Day and World Meteorological Day to everyone.
Yeah, thank you very much, Ms. Prakriti. Yeah, I think with that, we are at the end of our today's webinar. So I also like to thank all the organizer and the participants who gave your time for this webinar. So Dheeraj sir, do you have anything to share at the end?
No, anyway, thanks to all the speakers, commentators, and as well as participants joining this special webinar for today, celebrating World Meteorological Day. And definitely we will be continuing such interaction programs, discussions. And as suggested by many of you, we should be continuing collaborating in this field. And now I can see that, lesson learned from Rocky Mountains, Canadian Rockies, especially data from Peyto Glacier, we can at least, develop some experiments, models, and then also replicate in Nepal Himalayas also. And as suggested by Professor Kayster and Professor Arial, we do also have some data from glaciers from Nepal Himalayas. So we should continue exploring them and continuing the observations. And definitely we are honored to have Scott Munro during today's webinar, and also thanks to Prakriti Gurung from UNESCO for her tireless effort coordinating, communicating, and for her closing remarks. Thanks to all, and we'll see again. Happy World Meteorological Day. Namaste to all of you.
Yeah,
Okay,
thank you
namaste.
and bye-bye.
And congratulations to Professor Rizan Kayster.
Okay, thank you.
Yes.
See you tomorrow.
See you tomorrow.
Okay,
We will see you tomorrow.
Such a pleasure talking to you.
Everything out. We are
Okay.
welcoming you.
Okay, good.
Oh,
Thank you, Scott.
Okay, thank you. Bye-bye.
Bye,
okay.
Scott.
Okay.
Night.